Good day and welcome to our class on real analysis. In today's class, we'll be looking at another way of proving the uniqueness of the limit of a sequence. We'll be looking at another way of proving the uniqueness of the limit of a sequence. So we want to prove that the limit of a sequence is unique. Or better yet, you can state this as proof that a convergent sequence has a unique limit. So we go straight into the proof. In order to prove it, let A and B be the limit of the sequence A or A subscript n. This implies that our sequence AN converges to A and also sequence AN converges to B. Assume A is not equal to B. If A is not equal to B, it means one is greater than the other. So let our A be greater than B so that our A minus B will be greater than 0. And if A minus B is greater than 0, what do we want to show? We want to actually show that A is equal to B. By definition of convergence, we know that what? That a sequence is convergent, or that sequence AN will converge to A if for any epsilon greater than 0. We know that sequence AN will converge to A if for any epsilon greater than 0, there exists what? There exists a K1 belonging to the set of natural numbers such that the absolute value of A subscript n minus A is less than epsilon over 2 for all n greater than or equal to K1. Why are we using epsilon over 2? Because we need the distance between these to be as small as we can get. And if our sequence A is also converging to B, if sequence A is converging to B, then by the definition of convergence, it also means that for any epsilon greater than 0, there exists a K2 also belonging to the set of natural numbers such that the absolute value of AN minus B now will also be less than epsilon over 2 for all n greater than K2. For all n greater than K2. Now we want to bring out the distance between our A and B. Let's say the absolute value of A minus B. The absolute value of A minus B. This will be equal to what? The absolute value of A minus AN plus AN minus B. It's still the same thing. It's still the same thing. That's still the same thing. And we want this to be true for all n greater than K. We want this to be true for all n greater than K. For all n greater than K, where our K rather, is the maximum of our K1 and K2. Now let's see what happens to A minus B. A minus B, we have said it is A minus AN plus A subscript n minus B. And this is the same thing as A minus AN plus AN minus B. This is the same thing as minus 1 into AN minus A plus AN minus B. Absolute value takes care of the minus 1. This is the same thing as AN minus A plus AN minus B. But our AN minus A is less than epsilon over 2. This now is less than epsilon over 2. And also that is epsilon over 2. So our A minus B is less than what? Is less than epsilon. But we have said our epsilon is what? For all epsilon greater than 0. So let's assume I want to take epsilon greater than 0 or epsilon equal to 0. Since epsilon is greater than 0, then for all epsilon greater than 0, we have A minus B to be equals to 0, and our A is equal to B. This means that what? This implies that the limit of the sequence is the same. That tells us that the limit of a sequence is unique. The limit of a sequence is unique. You can compare this one with the previous video. Choose whichever one you think you can work with and use it when you are told to prove the uniqueness of the limit of a sequence. If you have gained anything in this video, or if you think this video is useful, give it a thumbs up, like, and share with your colleagues. Thank you. God bless you. I see you in the next video.